Good afternoon, everyone.
Good afternoon, sir.
Good afternoon.
How you doing, sir?
Hello.
Good morning.
We're good. So welcome to Cal 1. Am I in the right place? I'm in the right place. Welcome to Cal 1. Let's see, we've got 26 students here. I think we have, how many enrolled? Let's take a look here. Just want to give people a little bit of time to get here, just in case they're having trouble. 29 students enrolled, 26 are here. So I think we can get started. So welcome, and first things first. I am aware that there's an issue now getting to the electronic website stuff for Cengage or WebAssign. I just got off the phone with the publisher representative, and they did confirm that it is an issue on their end. So they're working on it, and hopefully by the time class ends, it'll all be up and running again. We'll see. It's been a bumpy start, to say the least, but I think things will start to level out here. All right, so let's get going. I sent out an email that had a link to an orientation video. I hope you all got that. Yes, most of you, yes. Okay, so in that video, I kind of gave a general rundown of how the class is going to work. If you did not watch that video, there's a link to it here on the main page of our Canvas shell. Here, let me switch over to student view. So there's the orientation video. Here's the link to the Zoom, which you're here, so obviously that worked for you. Link to the schedule, the ebook link once that's working, and then the lectures that we're recording here will be posted in this link, and then all the solutions to the homework problems are going to be there on video also. So with that said, are there any questions over anything that I covered or didn't cover in the orientation video that I can kind of address right now?
I had a real quick question.
Yes.
I see there on the to-do list on your screen, it says something about exam 2, and it says it's due on the 25th.
Yeah, what in the world? Okay, so that must be an assignment. Hold on, let me leave this view. I think somebody else brought this up also. Did I have an assignment? Yeah, I need to get rid of that. See, let me just delete this because it's not relevant. Okay, it's gone. Thank you. Let me go back to my homepage, see if it went away.
That would have been terrifying.
Yeah, we have an
Exam
exam tomorrow. Exam 2 over exam 1. You already missed it. Yeah. Okay, there, it's gone. All right. So any other questions?
In the orientation video, I know you said something along the lines of you want, besides your actual camera, you want electronic software, whatever. So we're not taking the test through Canvas. Are we supposed to print it out a hard copy and do it by hand and then scan it in?
Yeah, let's talk about the exam, because I think that's the most important part of this. So I can be very clear on it day one, because some students get really mad when they find out how I do the exams. Your grade in the class is made up pretty much exams. You do have homework and quizzes, but that's going to be kind of a different sort of, I'm not quite sure how I'm going to do this. 15%. I will maybe give you some quizzes in class. Maybe it's a participation grade. Maybe it's a, hey, do this problem, submit it to me next time, and I'll give you a Dropbox link to upload your work. But most of your grade is exams. So it's important that you understand what I'm going to expect. So let's actually go through that in detail. When we come to take an exam, what's going to happen is we're all going to come onto this Zoom session just like this. And then once everyone's here, I'm going to email everybody the test. And then I will give everybody about 10 minutes or so, maybe 15 minutes to either use your printer. If you have a printer, print the exam. If you don't, you'll have to handwrite the exam, all the problems. You have to copy it all from your computer screen to paper. Once you're done with that, you will send me a little chat in the Zoom chat, and you'll say, hey, I'm about to start my test. And at that point, you have to have your camera set up properly. And by properly, I mean that picture of me right there. You see that picture of me? Same shirt, actually. That's an example of what I'm expecting. So I expect to be able to see like what's around you, what's in front of you. Now, as far as the computer, you can have computer screens in front of you, but they must be turned off. All right. So you're not going to be doing anything on the computer during the exam. So to be fair to everyone and to have a level playing field, everybody has to have their camera set up properly. You can't be like, oh, well, I can't quite move this here. Or I know there's some like iPads that have like tracking, face tracking on them. So like, even though you get it set up, it starts to try and track your face. That's not an excuse. You have to figure out a proper setup so that I can see you in your workspace. I will take some time maybe before the test comes where I can say, hey, if you want to show me what you plan on doing with your camera, go ahead and do it now. And if you have a laptop, you can just move your laptop where the camera can see you. If you have a desktop where you can't move it around, I recommend you download Zoom on your phone and just use your phone as your camera during the test. Just make sure you plug your phone in so it doesn't die during the test. And then what you'll do is take the test, okay? Handwriting, right? Doing all the problems. So, oh, I forgot to mention, when you start the test, you send me the chat telling me you're going to start, set up your camera, and then you have to show the camera like every single page that's in front of you. So that means you'll show me the handwritten test that you just copied. Any blank paper, you have to show me like both sides of each blank paper. You have to show me any formula sheets you have, which you will be allowed some formula sheets. You have to show those to the camera. And then at that point, I know that everybody has the right thing in front of them, right? And not the wrong thing. You can't be working out of a spiral. You can't be working on a tablet. Everything's got to be handwritten, paper, pencil, old school style, right? Then once you finish the test, you'll send me another chat and you'll say, I'm done. Okay, when you're done, at that point, what you'll do is so you say, I'm done. And then once that comes through to me, I'll see the time that you finished the test, right? So let's say that's at, I don't know, 2:45, you send me a thing saying you're done. Well, I guess that wouldn't work because we end at 2:40. So say at 2:30, you say I'm done. At that point, I will give you 10 minutes. You can log off of Zoom, you can leave, you can vanish, but you then have 10 minutes to somehow get all that handwritten work to me, sent to me as a single PDF file. And that means you'll either have to scan it, if you have a scanner, or if you don't have a scanner, most students will take pictures with their phone and then convert those pictures into PDFs and then convert those PDFs into a single PDF. Now that's going to take some time to learn. So there will be an opportunity before the first exam to practice that. Maybe next class, I'll give you a little assignment where I'll send you a Dropbox link and I'll say, hey, send me multiple pages. Maybe if it's a copy of your notes, or maybe I'll give you a quiz problem, who knows? And that way you'll have a chance to practice this before the first test. Because the first test comes, got to have the camera set up right. You got to send me your work as a single file. You got to do that within 10 minutes. If you send it to me 30 minutes later, I can't accept it because I don't know what you've been doing for 30 minutes, right? You could have been accessing answers, referencing things you weren't supposed to. So just to be fair to everyone, the rules have to be adhered to strictly.
Professor?
Yes.
I did have one little thing to throw in when it comes to, because I know you said compiling all the photos together in one big PDF. Sorry, I got the dog shaking in the back. I know you said I know that could be pretty confusing and difficult. One thing one of my previous professors showed me is an app you can get on iPhone and Android called Cam Scanner. Mm-hmm. And there's an option, it's called batch. And it's you just click that, you take the picture and it does this weird thing where it actually makes it more visible if you have poor lighting or whatever. Mm-hmm. And it'll compile them all into one PDF and you can actually submit it to the Canvas app via the Cam Scanner app.
Okay.
So,
Yeah, I'm very familiar with the CAM scanner. I'm going to give you a Dropbox link to upload your work.
okay, well,
So it's going to be a
that
little
too, like,
bit.
you can also send it via to like Dropbox or anything too.
Yeah.
I think
Okay.
it helps if you have the Dropbox app though on your phone.
Okay. Yeah. So we'll practice this, and obviously there's people, some of you have already had to do this, so you've got it down, which is great. But if there's anyone here that is not sure how to do it, there will be that opportunity to ask questions. All right. And I'll walk you through. We'll try it with, on your phone. It'd be great if maybe you do that during the office hours, but we'll try and find some time here. Thank you, Jake. Okay. Any other questions or anything right now?
Yes, sir. I have one question about the exam.
Mhm.
Let's just say there's a graph. Do you want us to draw the graph and everything? Because I don't have a printer.
Well, yeah, that's going to be a little bit tricky. If there is, I try and make my test so that if there is a graph, it's something that won't take you too long to copy. Right. But yeah, if you don't have a printer, you'll have to copy it down. It's just one of the inherent problems we have here with doing this way, right? Just certain things are not easy to do. Did that answer your question, or?
Yes, sir.
Oh. Okay. Anything else?
Like, how many questions, like, on average would we get on an exam?
All right, that's a difficult one because it just depends on the exam and what material's on there. Now, what I will do is provide a review that will help, but I have to say that, reviews are one of those things I have to be real careful with, because I want you to get better at studying for tests rather than somebody just giving you kind of like a sample test, because really college is about, as you move through your major, college is really about how you take all the information you've learned and then somehow organize it here and then be able to kind of like perform on a test without somebody just like holding you by the hand, showing you, oh, be able to do that. So I will give you reviews to help you, but I may not give you the answers. The reviews may just be guides. But to answer your question, when you get the review, that'll give you some indication of the length and scope of the test.
I mean, the only reason I asked was just because I always worry a little bit about how much time I have to take the test to complete it. Because like every single time I took a test for college algebra and pre-cal, it was like right before,
Yeah, that's gonna be very, very kind of hard to predict. Some students will just crank it out and others will need the full time. I mean, there's some students where if I gave them 3 problems, they'd still take the full time because they'd sit there and go back and look and go back, so I mean, everyone is different. But I will say this, part of this class is not just you being able to demonstrate what you know, but also demonstrating what you know in an efficient amount of time. So, maybe you could do the problem, but it takes you half an hour, where on average, I would expect students can do it in about 10 minutes. So if you're one of those people who take a lot of time to get through the ideas in your mind, that could hurt you, because part of this is me assessing how efficient you are. And that's just because that's the way the calculus sequence is, right? I mean, think about it like in the real world, right? In the real world, if you're an engineer and your group comes up with, hey, we got to do this, you're going to go work on that, you're going to go work on that, you're going to work on that. You want a team that's efficient. You don't want someone that gets the right answer but takes them 3 weeks to do it, right? Like, you need someone who's going to get to it, get it, so this is part of training you to just process information better. So unless you have some special accommodation that you would know about, and I would probably be informed about, other than getting extended testing time because of the special accommodation. If you don't have that, then everyone is kind of being tested on time and efficiency. So I make the test, normally I make the test where I make the test, I take the test, I time myself, and I have to be able to be able to complete it in about 1/5 of the time it would take you. So our classes are 100 minutes long. Any test I make should not take me more than 20 minutes. I should be able to do it in 20 minutes. If I can do it in 20 minutes, then me asking you to do it in an hour is, I think, fair. That's kind of like the rule of thumb I've used for Cal 1 for a long time.
Alrighty, just making sure.
Well, I hope that addressed your question.
Yes, thank you.
Okay. Anything else?
Yes, sir. I have one more question.
Mhm.
Is the time that we have to write all the problems out, is that included in the time that's given for the exam, or is that excluded from the time?
Well,
of the
we
exam?
have 100 minutes in a class, except for the final, we have 100 minutes for each class. So, I mean, I have to factor that in when I make the test. I realize that the first 10, 15 minutes are probably going to be wasted on copying everything down. So I can't make the test as long as I normally would if it were like a face-to-face class. So I factor that in.
Yes, sir.
Mhm.
I have a question, sir, and this can deal with both our regular class and with exams. Because since this is online, what is like your policy with like Wi-Fi cutting out? Because I've had professors in the past before, like during regular class, if like your Wi-Fi cut out and you were kicked out of the class, like you wouldn't be allowed back in.
Yeah.
And I don't know, like if it matters with the class, but also if it happens to a student during an exam.
Yeah, that's a tricky one, you know, because if your Wi-Fi cuts out and you're gone for like 3 minutes, that's one thing. But if your Wi-Fi kicks out and you're gone for half an hour, then we get to a point where you probably are going to have to do a retake of the test. Now, during class lecture, if you know, this is optional. You being here is up to you, right? Like, if you want to come here and learn, ask questions, that's what I'm here for, right? If you're not attending, you know, I'm not gonna. If you come in and leave, whatever, you know, I don't babysit. So for regular classes, I'm not so concerned. It's really just for tests. So I'll work with it. It'll be situation by situation, and it'd be kind of weird if like every class you were here, you never had any issues, and then the test day, your Wi-Fi is gone. You know, I mean, it could happen, but it would just be a little strange. We'll work it out. Don't stress out about it. All right. Let's talk about bonus. Everybody likes bonus, right? So the homework is part of your grade, but obviously it's very difficult for me to collect homework, right? And the fact that I post the solutions to the homework, right? There's no real sense in me, the video solutions, right? Of me working through the problems. There's no real sense in me grading them, because if you watch my videos, you're gonna get them right. So really the homework is for your own practice, right? And so what I recommend you do is you keep all your homework in one place, in like a binder or a spiral folder. And at the end of the semester, I'll do something where I maybe ask you to like just show the camera all your homework binder, and then I can give you some sort of credit for that. So keep your homework in one place. Know that that will help you later on. And then the other bonus, it has to do with your video feed. So during the test, you have to have your video on. Other than that, I don't need you to have your video on. However, if you have it on, that is going to count as bonus for you. So the way it'll work is every day I'm going to be calling students. I have a list here. This is where everyone's videos start to come on. So I have a list here of everyone's name. And what I'll do is I'm going to call on students every day. Okay. I'm always going to be calling on people. And I'm also going to be looking who has their videos on. So I will be keeping record of who's streaming and who's not. And what I'll do is at the end of the semester, I'll look at, you know, how many times did we meet? And how many times did you have your video on? And you can earn up to 8 points on your final exam. That's almost a full letter grade. Now, so that means if every day you had your camera on, you can get 8 points. If half the time you had your camera on, right, half the days, then you get 4 points. Make sense? So that's completely up to you, and it starts today. So yeah. Hello, everyone. Now I'm starting to see faces. This is better. So I have the way that I do this, I have a monitor here that I can write on. Okay, pretty big monitor. So I'm going to be writing on like I'm going to be using OneNote and be writing, talking. That's what you'll see. But then I look up and I have a monitor that's just students, right? So I like to be able to look down, write, look up, ask a question, and then see people like react, right? If you're sitting there like going like with that oh shit look on your face, like what is he doing? You know, then I know like maybe I need to look at that again or talk about it a little different, you know, just like it would be face to face. It just really helps me. So that's why I encourage that. Remember to always pay attention to what you're doing on camera, right? Make sure you're, you know, right. I mean, this is just part of what's happening nowadays. You see these funny videos of people that didn't know their video was on. And so just be careful. All right. Anything else?
I have one last question. It's about the graphing calculators. Are we allowed to have one of those? And if we are, what type would you allow?
Yeah, good question. So yes, you're allowed to have a graphing calculator. You're not required to have one. You need a scientific calculator for sure. So something that does logarithms, you know, sine, cosine, tangent. Graphing is up to you. It could help you if you know how to use it, right? But there is a restriction on the graphing calculator that you cannot use one that has a computer algebra system in it. And the only ones that I'm aware of right now that have that are the TI-89. That's the one I have, the TI-89. That you cannot have. And then the TI Nspire, but it has to say CAS in the top right corner. So there's an Nspire that doesn't have CAS, and there's an Nspire that does CAS. So the CAS you cannot use. Now, that's because you probably, if you ever take a standardized test, like you have to take a SAT or something, you know, some standardized test, most of the time you won't be able to use that. So very few institutions allow those calculators on tests. Now, I wouldn't, if you're like an engineering major or, you know, really like physics or something, I recommend getting one. But that's kind of your other calculator that you'll use, you know, once you've like progressed to a certain point. It's a great tool to have, but not here. Does that answer your question?
Yes, it does. Thank you.
Okay.
So I have the Inspire, but it's just the Inspire CX.
CX is fine.
And then I also have the TI-84, but it's the plus CE.
That's okay.
Okay, cool.
Yep. As long as it doesn't say CAS, that stands for Computer Algebra System. As long as it doesn't say that, and as long as it's not a TI-89. So I don't know if you're familiar with what those calculators do, but
I was going to ask that. What does that actually mean?
So like if you go to a graphing calculator that does not have CAS, and let's say, just to give you a quick example here, where's my pen? So like a standard graphing calculator, if you were to type into that calculator x squared minus 4 and hit enter, what it's going to do is it's going to look into the memory of the calculator, and it's going to look at whether or not it ever had a value given to it for x. So like maybe stored in the memory of the calculator, the last time it did something, x was 2. Let's say x was 5. Okay, so if you hit enter, what it would do is it would say 5 squared minus 4, and it would give you a numerical answer, right? 21. That's what will happen on a standard calculator. On a CAS calculator, you have the ability to type that in and use a function called factor, and it will actually do the difference of squares for you. So it will factor it, and it'll do that for very complicated expressions. And everything we're going to learn how to do in here, which the main idea is this thing called taking the derivative of something, a CAS calculator can do symbolically. So it's very, very powerful. So that's why I say if you're a physics major, engineering major, I recommend getting your hands on one for future reference. But for learning it for the first time, it's not, it's cheating and you're not going to learn it. So you're just going to be relying on the calculator to do it and never actually learn anything. So I hope that that makes sense. Computer algebra does symbolic manipulation, which is a huge deal. Okay. We good?
I have a question.
Yes.
Hello, can you hear me?
Yes, I can hear you.
Okay. Can we use our calculators on the test?
Yes. Mhm.
Okay.
Yeah. But I will say though that in this class, when I'm giving a test, when I see students that are just sitting there like this, that usually means that they're lost. Okay. Because mostly everything we do here is something mechanical with a process that requires a manipulation by hand. If you're sitting here like this, that means that you're trying to look at a graph, you're trying to figure something out, and it really is kind of like, it shows that there's some desperation. The only computations you ever have to make, you can do on your calculator quickly. Like if there's something like you have to square something or take a square root, it's very quick. But if you're sitting there for most of the test just like this, that really is an indication to me that you're pretty far removed from what the main idea of this class is. You'll see as we get through things that I'm very seldom am I going to pull out my calculator for any significant amount of time. But they're allowed on the test. Okay, are we ready? Okay, so your homework assignments are going to come out of the ebook, which I know at least when I started this class, you can't get to the ebook. So if it's still not working today, I'm going to email everybody a copy of the homework problems to do. And so what you'll be doing is following this schedule. And so today, what we're supposed to cover is we're going to start here today, Tuesday, August 24th. We're going to start with chapter 1, section 3, the limit of a function. And the homework problems you're supposed to do for that are numbers 4, 5, 6, 7, 8, 9, 13, 15, 17, and 19. So if the WebAssign thing does not come back, I will send that out to you shortly after class. Okay?
Yes, sir. Also, will you send the access code because it requires it?
You should not need an access code.
Last night, well, Monday, yesterday, Monday, when I did the sign and everything, it said I had to have an access code.
Yeah, I know. I think it's been fixed. Has anybody been able to get in?
I was able to get in one day, but it asked the same thing about an access code, and then I was able to somehow find it somewhere else, but it told me I was only allowed to view it until September 2nd. I would only have like 14 days to be able to access it.
Oh yeah, it's saying there's a trial, like a 14-day trial.
Yeah, 14 days. I'm aware of that. I think I sent an email out to everyone to ignore that. So I don't want to spend too much time on this. Canvas, right? Canvas is where we go in right here. This is Canvas. And this whole idea of being able to click in here and it sends you to the ebook and to all that, that is called integration of Canvas into WebAssign into Canvas. I have avoided that for the last 4 years. Okay, it's been there for about 4 years and I have avoided it because I wanted to make sure it was reliable before I started using it. This is the first semester I've used it and it's a freaking joke. I mean, it is, I'm just so frustrated because here we are. It's like you can't even get to your damn materials on day one. The whole idea is that you pay in your tuition for access so that day one you have access, and here we are without access. So I'm as frustrated as you are, but I can't really do anything to fix it at this point. So I'm hoping everyone who needs to know knows about what the issues are. I'm just going to hope that it gets resolved. I will work with you as much as possible to make it easier for you. You know, send you the homework problems, things like that. Look, in all honesty, You don't really need the ebook, okay? If you come to class, I will answer questions, I'll go through the concepts. I mean, how many of you actually read your math book anyway, right? Not to
I
say
do.
you don't.
I read mine. I really do.
Yeah, some do, right? So it is important, but you will be okay for the start of the semester while we get things off the ground here. The homework problems I'll get to you. I've provided the homework solution videos. Let's just make the best out of it. Know that it's being addressed. If you want a copy of a few of the sections like pages and you can't get to the ebook, just email me. You know what? In fact, I'll try and make a copy of the first section. How about that? And I'll just send that all to you. Daniel, just so you have it.
Yes, sir.
Okay.
Thank you.
Okay. I mean, let me just write a reminder because I have a whole list of things I need to do. Email. 1.3 book and homework. Okay, I'm going to send that. All right. I don't want to waste any time. I was going to have someone share their screen so that they could show everyone how to get into the ebook, but I seriously don't think it's working, so we're not even going to do that. All right, I think I'm ready to get started. All right. We're going to start with 1.3. There are two other sections that I'm not covering, functions and essential functions. Now, I've provided the notes in Canvas for you to look at those if you want to look at them, the notes that go with those sections. And there are homework problems over here that you're welcome to do for those sections, but I do not believe I have video solutions for those. But this is all review concepts from college algebra, pre-cal, leading into Cal 1. So we are starting with 1.3. So here we go. So before we begin, let's talk about, you know, your path to this point, right? Everyone here should have taken some sort of college algebra. Hopefully you took like the STEM version if you did it at Northwest Vista. And then everyone should have gotten through pre-cal successfully, right? And here we are. So the way that this is going to work is like pre-cal, really the big thing about pre-cal is it should have like raised your bar up as far as like, maybe like you should have matured, like mathematically matured in pre-cal. It should have been this process where you became a better math student. In terms of what we need for Cal 1 from pre-cal, everyone needs to understand the unit circle. Okay, so like if I say what's cosine of 30 degrees, there should not be, hold on. Cosine of 30 degrees is not in the calculator. Cosine of 30 degrees should be up here. So you should be like visualizing a unit circle. You should be looking, cosine is the x coordinate. And so what's the x coordinate of 30 degrees?
I still got to look at the unit circle.
Over 2.
So square root of 3 over 2. You might have to look at the unit circle. The unit circle is not on your formula sheets. Okay, that I let you have formula sheets. The unit circle is not there. Okay, so you need to, there is a way that you can, I'm not a big person, like I'm not a memorizer. Is that the right word? I do not like to memorize things, okay? My brain doesn't work that way. But the unit circle has a structure to it that makes it, if you understand the structure, you can really learn it easily, okay? You want to get to that point. Maybe you're not there. I'm just telling you what you need from pre-cal that's going to make your life easier here. Knowing the unit circle, knowing the value of the trig functions at the common angles will help you tremendously. So if you're not there, it's okay. That's something you might want to write down, need to go, you know, redo that, be ready. And then the other thing is solving trig equations. So things like, you know, a trig equation would be something like this. If you're trying to solve like sine, let's say sine theta, let's say 2 sine theta minus 1 equals 0. Like that's a trig equation. And if you're asked to solve this, then you need to figure out what values of theta would make that true. So being able to solve trig equations is an essential concept. It's not going to come up till later, but when we get to it, it's not going to be this huge review of it. It's going to be like, remember in pre-cal when you did this? Okay. All right. So that's the second thing. Knowledge of the graphs of the trig functions, like what sine looks like, what cosine looks like. what tangent looks like, what the natural log looks like, what d to the x looks like. So all your like basic functions, you need to have some sort of grasp as to what they look like, right? But really, Cal 1 is kind of its own animal, all right? Like we're not doing stuff we did in pre-cal. We're not doing stuff we did in algebra. All of that was just build up and like putting tools in our toolbox to actually be able to do something with that information. So calculus is where we actually first start seeing how we can apply this math to something that would relate to the real world in a meaningful way, all right? So you've got all the tools in the toolbox that you need, hopefully, and you've got a mathematical maturity that's told you that you've learned, I must do my homework to really be able to understand this. And now we set forth to figure out what this thing calculus is all about, right? You've all heard of it. Some of you have seen it, but calculus is actually, I've always said Cal 1 is a very simple idea that's difficult to execute. Okay, so the idea, the concept is something most people will be like, oh yeah, I understand. But executing it is something else. So let's talk about the idea, all right? What's the main, if there was like a main idea in calculus, here's what it would be. Like I said, it's a very simple idea. You have a graph of a function, all right? So let me just put a graph here. Just making something up, right? In college algebra, we learned how to graph functions, right? We learned what a function was, vertical line test, right? Horizontal line test to check to see if it had an inverse, you know, all these things we learned, different types of functions, polynomials, rational, exponential, logarithmic, sine, you know, trig functions, all these different functions we learned. Here, we're just looking at some generic function, right? And the idea is that if I were to go, let's say, let me kind of redraw this. I'm going to change something, sorry. Not too much, I'm just going to change something very subtle. I'm actually going to have the function start at a point and end at a point, okay? So if I were to ask you right now to connect these 2 points with a straight line, you could visualize that, right? Pretty easily, right? 2 endpoints, connect them. Now, if you actually knew what those 2 points were, like let's say I had told you what this point was, x1, y1, and I had told you what the other point was, x2, y2, then you learned in college algebra that you can actually find the equation of that line, that green line, right? There was a formula in college algebra. It goes like this, y minus y1 equals m times x minus x1. This was called the point slope formula. That look familiar? If somebody gives you a point, right, a point on a line, and they give you the slope of the line, then you can come up with the equation of the line. So do we have a point? Do we have an actual point on this line? Sure, there it is, right? I gave you a point, right? There's 1 point. Do we know the slope of that line? Well, not explicitly, but could we find it? Do we know, is there a formula for the slope of a line?
Yes.
Yeah, it's rise over run, right? That's the slope of the line. But in terms of 2 points, it's y2 minus y1 over x2 minus x1. Does that look familiar to you? Right? So again, if you have a function and you have 2 points that are given to you, then you can always find the equation of the line connecting those 2 points. That's nothing new, right? That's, I would say, basic algebra stuff, right? So what's the calculus then? Well, the calculus is this. The calculus takes that same picture but instead of taking 2 points and connecting them with a line, it takes 1 point, okay, like that. I'm just going to take that point. And then it takes we take a second point, Okay, I'm going to do it in gray. Now, everyone understand that if I connect these two together, I can find the equation of the line, just like the previous problem, right? But here's the catch. Here's what calculus asks you to do. It asks you to take that second point and move it along the curve, move it along the curve, move it along the curve, and then put it right on top of the other point. So can you visualize what that would be? Maybe you can't, so I'm gonna help you. Let me open something up. Sorry, I thought I had it opened, but let me just open it real quick. There we go. Kind of getting ahead of myself here, but okay, let me make this bigger for you. So again, imagine having a point on a graph and then a second point, and then connecting those two with a straight line. That we could find the equation of that line because we're given 2 points and it's very clear that we could find that equation, right? But we're trying to move that second point closer and closer to the first point. Now, do we have a line there? Is there a line between those 2 points? Yeah, okay, and as I move closer, still have a line between those 2 points, right? Still have a line between those 2 points, still have a line between those 2 points, still. Let me zoom in a little bit. Okay, so now I'm zoomed in, still have a line between those 2 points, still, and then what happens? I put them right on top of one another and we have an issue. What's wrong? Something happens when we put the 2 points on top of one another, something dramatic happens. So think about what we wrote down here. Okay. The slope requires that you have a change in y, right, divided by a change in x. If the 2 points are right on top of one another, what's the change in y? What's the difference between the two y coordinates if it's the same point?
0.
0, right? So you have no change in y, and you're going to divide that by, well, what's the change in x if there's same 0,
Also
0,
zero.
right? And 0 divided by 0 is undefined, right? That is undefined. And so we have a problem, all right? We have a problem. So geometrically, the essence of what we're going to try and do in this class is to take a point, take another point, slide it along the curve and move it and put it on top of the other one and try and figure out if we can find the equation of that line. Now, I'll explain why we would want to do that, but that's really just like geometrically, that's all we're trying to do, all right? Let me go back to that picture I had again. Okay, so this one here. Okay, so I just want everyone to think about this. If right now, if we were to freeze that, I'm going to try and draw. You know what? I can't draw on that. So yeah, I'm not going to be able to do this. I'm limited a little bit here. Try one more thing. I've got too much technology sometimes. Just got to close this program down, reopen it and see if it works. There it is. Okay, that line right there. Okay. Now, obviously, those 2 points are not on top of one another, right? They're not on top of one another. But now I'm going to move that second point closer, and I'll have a different line, right? That's a different line. And I could kind of show you what that one looks like. And then if I move it a little bit closer, I have a different line, right? Now think carefully about what I'm going to ask you to consider at this point. As the blue dot gets closer to the black dot, the lines, I'm creating like a sequence of lines, aren't I? That sequence of lines are approaching one specific line. Like they seem to be getting closer and closer to something. Like as I move it, as I get closer and closer and closer, like that is really, really close to what the line, right? If we put the 2 points right on top of each other, there's like, it's like really close to it, but not quite. I'm a little bit off. I guess what I'm saying is it definitely isn't that line, right? And it's not that line. It's, you can kind of see the pitch of it, can't you? You can kind of see that pitch. So it's like there has to be an answer as to what that is approaching, but we don't know what it is because once we get the 2 points on top of one another, we no longer have a slope and we have chaos. Does that make sense? Any questions on that? If you're really lost, don't worry. We have plenty of time to understand this, all right? I'm just trying to give you just like a visual idea of what we're going to be going for here. So why would we want to know this, right? Why would we ever want to know how to figure out the equation of some line on some curve? Well, here's why. Think about this. Let's say this is time. And let's say that this is distance, right? So let's say you're about to drive to go, I don't know, up to HEB to get some food, right? So you start here at the origin. That means at 0 time, you've driven 0, let's say miles. Let's do this in hours. Okay, so at the beginning of your trip, 0, you've gone, no time's gone by and you haven't gone anywhere. Then you start driving, right? You drive and speed up, slow down, speed up, slow down. And you eventually get to the end of your trip. Here you are. And 1 hour later, you're at HEB and it was 20 miles because, I don't know, there's a lot of traffic. Okay. So what was your average speed? What was your average speed? So what was your average speed?
20 miles.
What is the definition of speed? It's our average speed.
Distance over time.
The distance you travel. Distance divided by the time it takes you to do it, right? So for this particular trip, the average speed would be what? So how far did we go?
20 miles.
20 miles. And how long did it take us?
An hour.
1 hour. So our average speed would have been 20 miles per hour, right?
Yes.
I'm just going to put MPH. That would have been your average speed, 20 miles per hour. Yes?
Yes.
Now, geometrically, you may not have realized this before, but that average speed is actually just the slope of the line connecting the two endpoints. Because think about what this is. From here to here, that's your rise, isn't it? Which for us would be 20, wouldn't it? Because you went from 0 to 20. And then this distance here would be your run, and that would be 1 hour here. So the slope of the gray line, right? The slope of the gray line is actually 20 over 1, which is 20, which exactly matches your average speed. It's not a coincidence. That is the actual relationship. That the 2 points at the end, if you connect them with a straight line and find the slope of that straight line, that's equivalent to the average speed on the trip. Understand that? So now let's go back and think about what I was asking before this, all right, with the calculus idea. The calculus idea wants us to go to some arbitrary point, right? Grab the other point and move it on top of that first point. What would that correspond to physically in this situation?
It's telling us what our speed was at that specific point in time.
It's the speed, exactly. It would be representative if we could somehow figure out what that line is, right, through one point, which doesn't make any sense at all. But if we could somehow wrap our heads around this idea that there is a line that it's headed towards, whatever that slope of that line is would correspond to the speed at that instant in time. The speed at the instant in time. And we know that when you're driving down the road, right, driving to HEB, yes, it may have taken you an hour to go 20 miles, but that doesn't mean every time we look down at the speedometer, it said 20, right? Maybe we were doing 30, maybe we had to come to a stop. So your instantaneous speed is different throughout the trip. Being able to find the slope of this, right, if we could somehow find the slope of that, that would give us our instantaneous speed.
Is that what a derivative is?
And that's what the derivative will allow us to do. Okay. So if you don't know what the derivative is, it's okay. We got to build to it. Okay. But that's exactly what the derivative allows us to get, is that slope of that line. Okay. But we're going to have to do quite a bit of work to get to the derivative. So we're not there. All right. Instantaneous speed. And that's a big deal because the idea of speed, think about this definition of speed again. Distance over time. Distance divided by time is what speed is, right? So if you're running, right, and then you say, you know, right there, like clap your hands at that instant, like I'm running and right there, okay, how fast am I running? There's a problem with that because at an instant in time, I'm not moving, right? So I've gone no distance. And if I'm not moving because I'm frozen in time, no time has gone by. So the idea of speed kind of goes away because you have 0 over 0. 0 over 0 is a problem, right? We're not allowed to divide by 0 in our number system. So yeah, this was a big problem for a long time, is trying to figure out, is there a way we can define speed at an instant? And calculus allowed us to do that, all right? And that's what we're going to do. Now, any questions on that? Let's imagine now, okay, so I want you to kind of clear your mind. Let's imagine now that we have figured out a way to do this. In other words, we have figured out a way that if somebody gives you a function, you can go to any point on that function, let's call it A, and when you get to that point, you have now developed a way to find the slope of the line that goes through that point. Let's imagine that you can do that now, all right? Don't ask me how yet, but just imagine we have that ability now. You can go to any function, go to any point, look at the function, and you can find that slope of that line on that point, right? Then, how hard would it be for us to find that little valley on that function, okay? So if I wanted to find that lowest point, that little dip in the function, can somebody tell me what the slope of that line would have to be there? So if we're at the bottom point, what would that line that goes through that point, what would it have to be?
0.
0.
Yeah,
So can y'all see that line that would go through that one point would kind of have to be like this, right? So we have a way of finding the slope. And so if I want to know where that happens, I just figure out where that m equals 0, and where that m equals 0 is going to be able to tell me where I have that little valley. And that means that, and again, I'm stretching because this is where we're headed and we have a lot of work to get to this. But generally speaking, what's going to happen after we do that is that if we take any function, we are going to be able to find all the peaks and valleys of the function, which you could not do in algebra. I know in algebra, you had to graph functions, right? And you would find like x-intercepts, and then you even did this thing with like polynomials with multiplicities, and whether or not it like crossed or bounced and all this stuff. How many terms does it have? But what you could never do in algebra is actually figure out those highest and lowest points. You couldn't do it. There's no way you could do it. And that's because you didn't have calculus. Calculus is the tool that will allow us to find the highest and lowest points. That makes sense? For any function, for arbitrary functions. no matter how complex they are. Okay, so that's a very powerful thing. Y'all following all this? Does this seem pretty, I guess, simple as far as conceptually what the idea is? Yeah.
Yes, it is.
Again, the execution is going to be the hard part, but because it's going to require, well, execution, but it's also going to be a lot of algebra, and there's a lot of other things we need. But the idea is not hard to, I think, for most people to understand. Okay, so now we do that. Now, big deal. We can find the highest and lowest points on a graph. Big deal, right? Big deal. Okay, so let me give you like a final kind of problem, all right, to kind of bring it all together. Let's say that I want to build this will be a simple problem, but I think by me giving it to you, you will understand how this could be used in the real world. Let's say that I have a roadway, right? A straight roadway. And let's say I have a building over here, building A. And on this side, I have building B. Let's say that the roadway is 60 feet wide. Okay, so it might be more than 2 lanes, all right? It might be a couple lanes, 60 feet wide. And let's say that the buildings are, I don't know, 300 feet down the road from one another, okay? So the roads are 60 feet apart, 300 feet down. Go with me? I need to hire a company because my company owns both those buildings, and we need to connect those 2 buildings with fiber optic cable, all right? Because we're trying to, you know, whatever, we need to get them connected, all right? So when we put the fiber optic cable, we have to decide how we're going to do it, right? Like, how are we going to run the cable? One thing we could do is we could just run the cable directly from here to here, right? But if we do that, the local code says that we cannot go under the ground. We cannot go under the roadway because there's other things under the roadway. So we actually have to go above the roadway, right? And if we go down, we can go down like this and then go across like that. And when we go along the side of the roadway there, we have to bury it. Okay, city says we have to bury it. So we need to make a decision. How do we do this? Do we go directly across and go above the road, or do we go under the road and then go above the road here? Now, it's going to cost us a different amount of money to do it each way, because the cost to do it above the road, let's say to go above the road, I'm just making these numbers up, okay? Let's say to go above the road, it's going to cost us $4,200 a foot. Now, the reason why it's more expensive is because I'm just making this up, okay? Because to go above the road, our cable's going to be exposed to the elements, and we have to protect it more, and it's more expensive. The whatever, it's $4,200 per foot to run it above ground. Now, if we go underground, it's cheaper. It only cost us $3,300 a foot. Okay. The question now is, how do you run the cable to make it the cheapest way? Okay. To make it the cheapest way. How is that related to what I'm talking about? Like, how could that possibly be related to this, right? Like, how could it possibly be related to this? Well, let's see. Let me see if I can walk you through this. I could go this path, right, where it's all above ground. I could go all underground and then go straight across, right? If I do this way, connect it straight across, that's the longest distance. Would you agree? Or sorry, that's the shortest. I just said that completely backwards. That's the shortest distance, isn't it? Shortest distance between these 2 points is a straight line. But that's all above ground, which means you're going to be doing it the most expensive way possible, the whole way. Whereas if you go this way, it's longer distance, but part of it is cheaper, right? So the only part that's expensive is this part. This part's cheaper.
Yeah.
Y'all still with me? So which way do we go? Well, there's another scenario. Why do we have to do one of these two? Why can't we do this? Start here, go some distance, stop, and then go across. What's making us think that we have to go here, then here, or all the way down and over? Could there be some combination of the two in between? Y'all see what I'm saying? So watch me develop this, okay? You'll have to do this later. It's your first time ever seeing this, but I want to bring this all together into one final example. So let's say I'm gonna go with this model right here, where I'm gonna go down some amount and then over, and I wanna know how much that costs. So I'm gonna call the distance from here to here that I don't know, I'm gonna call this X, because I don't know how far I'm gonna go, all right? And I'm going to call the distance that would go from here to here, I'm going to call that Y. You with me? So how much is this going to cost me? The cost will be equal to, well, how much am I going underground here?
Wouldn't it be X times 3,300 plus Y times 4,200?
Yes, okay, so Maddie's saying that the distance from here to here is X, right? And if X is measured in feet, then it's going to cost us $3,300 for every foot. So it's going to be 3,300 X. That would represent the cost of doing this piece in green, right? That's this. And then Maddie, what were you saying? Plus what other cost?
Plus 4,200 times Y.
4,200 times Y. Do y'all agree with that? Because this is, let me get a different color here. I'm out of colors. Let's do that. That right there. That's the Y part, right? That's the Y part. And that's above ground. And so I've got to pay $4,200 for every foot. Good. Does everyone agree with that? Anyone have a question on that? The cost should be 3,300X plus 4,200Y.
Sounds right to
I
me.
have a question.
Yes.
What is C?
Cost.
Oh, okay.
I just made up, yeah, cost. I can just say it here, cost. So in order to know what the cost is for doing this, I need to take 3,300X plus 4,200Y. All right, well, in every class we've taken, the things we've been dealing with, the functions that we've been dealing with have been functions, excuse me, of X, haven't they? Like a function of a single variable. Here, in order to know the cost, I need to know two different things. I need to know what X is and I need to know what Y is, don't I? I'm about to resolve that issue. I'm about to rewrite this equation where all I have is X's. And watch how I do it. I'm gonna go back to the geometry of this problem. Let me erase some things to make it a little easier for you to see. We know that we have a right triangle right here. Do y'all see that right triangle? You'll see that right triangle right there? Why is this distance, right, from here to here? Does anybody know the distance from here to here?
It's
60
60.
feet.
60, that's the width of the street, right? Okay, so that's 60. Do you know this distance from here to here? Be careful.
300 minus X.
300 minus X. See, because X is how far we go down, right? X is how far we go down. So whatever's left is 300 minus X. So like if this was 100, that would be 200. If this was 50, that would be 250. So this is 300 minus X. Y'all good? Now what I have is a relationship between these sides. I have the Pythagorean identity, don't I? We have that like a squared plus b squared is c squared. So I'm going to write that down over here on the side. I know that 300 minus x squared plus 60 squared equals y squared. Do y'all agree with that? Just off of this right triangle? Now what I'm going to do is I'm just going to take the square root on both sides. And now I have an equation for y, don't I? I have the square root of 300 minus x squared plus 60 squared equals y. Now I should put plus or minus here because I took the square root on both sides. I should do plus or minus. I'm not
There's no
going
such thing
to.
as a negative length.
Yeah, y is the hypotenuse of this triangle. It can't be negative, so I'm not even going to look at the negative case. But watch, does anyone have a question on how I got that part? And if you're sitting here like blown away, like, holy crap, I would have never come up with this. I understand, that's not the point. I'm trying to show you how this whole idea of finding peaks and valleys is useful, all right? So I'm constructing a problem, a real world problem, to show you how we would use it, all right? So now what I'd like to do is I'd like to rewrite the cost function. I'm going to put cost equals 3,300x plus 4,200 times y. But y is this, isn't it? So times the square root of 300 minus x, that quantity squared, plus 60 squared. And look at that, everyone. We now have what you could argue to be a function of x. You could look at this cost now as a function of a single variable, right? All of this stuff here just has x in it, right? Right? My cost is a function of one thing only now. You tell me how far to go down, right? You tell me what that x is, and I will tell you how much it's going to cost you. So wouldn't it be nice if we could figure out where the highest and lowest points of that graph were? Because if this is our cost function, if we could find the lowest point, right, that would tell us where our lowest cost is. If we could only do that, right? Well, calculus will allow us to do that. We will be able to find the lowest point of that graph. Now I'm going to cheat and I'm going to use graphing utility to do it for me, just so we can leave here with an answer, all right? Because I'm curious, I made up the problem. So I'm not sure what's going to happen. I just completely randomly made this problem up. So the cost, I'm going to treat this like a function of x. I'm going to say cost equals 3,300x, right? 3,300x plus the square root of 300 minus x, that quantity squared, plus 60 squared. Someone can check. Is that correct? Did I write that right?
That should be 4,200
Oh, yeah.
times that.
Yeah, 4,200. I completely forgot the cost there. There we go. That look right? Was that our cost function? Okay. So again, that's how much it's going to cost dependent upon x. Now, one more thing I'm going to do here. Do we have a restriction on x? Is there like a smallest x can be and a biggest x can be? I'll go back to the picture.
It has to be greater than 0, but less than 300.
Yeah, I mean,
Greater than
0
or equal to 0.
Yeah, 0 would mean what? If x was 0, that means you're going straight across, right? All above the road, just straight across from A to B. The other extreme would be if you go straight down and then over, and that would be x is 300. So we only want to look at this graph between, so the way I do this, I say 0 less than or equal to x less than or equal to 300. And now it's time to look at the graph. Okay, you ready to see it?
Technically, would x necessarily have a maximum? Like,
oh, well, okay,
we
I know
didn't
what you're
want
asking.
to go past 300, but technically, could we? Or
You
would that
technically
screw up the
could.
equation?
You technically could, but you get fired, Maddie.
Yeah.
Right? Because if you go past 300, then you're obviously wasting resources, right? But yes, within the algebra of the problem, you could let x go past 300. But within the framework of the actual like physical problem and the money involved, anything past 300 wouldn't make sense.
Mm-hmm.
But good question, yes. Does everyone understand that question? Okay, here we go. Let's look at the graph. I'm going to have to zoom this thing out until I find it because I have no idea how much it's going to cost. Let's see if I can figure out where it is. Where? Oh, there it is. Okay, so it's somewhere between 120 and something thousand. So I'm going to change the x-axis to only go between 0 and, let's say, 400. I got lucky. All right, and then the y is going to go between 0. Sometimes I mess this up. There we go. That should work. There's the graph. There's the graph of that function. All right. So at 0, okay, if I were to let x be 0, look at that point at the very beginning. How much would it cost us to run that cable if we let x be 0? That means you go over the road, straight line to the other building. It's going to cost how much? $1,284,952, right? The other extreme would have been to go down 300, right? Go down 300 and then straight across the road. How much would that cost us? $1,242,000, right? But from the graph, can you see neither of those two ways is the best way to do it? The best way to do it is this way, right here. You go down 223 feet, and then you cut straight across. And if you do that, it's going to cost you $1,145,000. That's a significant amount of money, right? Because what was this over here? 1,242,000. That's almost $100,000 difference, right? And then over here, it's even more of a difference, right? So again, very simple idea here of a problem, a little hard to set up first time you ever see it. But if you go back to the initial kind of idea, if you were to have a if you were to have an engineering firm, right, that's trying to connect two buildings together, and they say, hey, we got to run a cable. And then you have one engineer that shows up and goes, oh, well, hey, shortest distance between 2 points, right? Straight line, boom. That's the way to do it because that's the shortest distance. That's wrong, right? You're wasting money. You're throwing money away. And if you're competing for that bid, right? Maybe there's another company competing with you. You want to try and find the optimum way of doing this to be able to make a competitive bid, still make money, but make a competitive bid. If you just do it a simple way like this, you'll never get the bid because you're going to be wasting too much of your resources. All right, I hope that gives you some idea of like the direction of what we're trying to do here in this class. We want to be able to do problems like this at the end where you're able to figure out, this is called an optimization problem, and it's one of the main goals of Cal 1 is to be able to optimize functions. Okay. Here we go. There will be lots of little detours and pit stops that we'll make on that journey to get to that endpoint. And there are a lot, I don't want you to think that that's all what Cal 1 is about, but that gives you a good flavor of it. We gotta start with the first idea though. And the first idea here takes us back to chapter 1. And it's the idea of what's called the limit. All right, let me evaluate this. How are y'all doing? It's 2:13, been here for a while. It's hard to sit there for this long, I understand.
It's good, man.
All right, here we go. So I don't want you to forget everything I just said because I do want you to kind of keep that as like where we're headed, but we have to kind of start with a clean slate here, all right? So what I want us to do is take a look at this function. The specific function I'm asking you to look at is the function f of x equals negative x cubed plus 4x squared. And what I'd like to know is what happens when you plug 2 into that function. Does that seem like a reasonable thing I could ask you at this point? To plug 2 in and you tell me what comes out?
Definitely.
Okay,
Yeah.
so what would you get? You plug 2 in. Anybody?
8.
8. Okay, good. We get 8. All right. So you get 8 if you plug that in. What we just did there is algebra, right? That is algebra. I gave you a function. I asked you to evaluate that function at the point 2, right? Plug 2 into the function, tell me what comes out. That is not what calculus is about. What calculus is about is like almost the reverse of that. What I want you to do is, instead of focusing all your attention, see, can you all kind of see the graph of this function in the background? When we say plug 2 into this function, all you're really telling me is what's happening when you plug 2 in, right? You don't care about anything else on the function. You just want to know what's happening at 2, right? That's all you're telling me. You're not telling me what's happening at, at 1 or at 3, just 2. So it's almost like you're just very narrow field of view telling me what's happening at 1 point. Calculus, what we do is we say, who cares what's happening at 2? I don't care what's happening at 2. I want to know what's happening near 2. Near it. Okay, now the word near should cause you some problems, all right? When I say the word near, this is very subjective. So, am I near you right now? Am I near you? I see a lot of people saying no. I'm not near you. I'm not close to you. I'm offended. I'm offended. You don't feel close yet? So
I thought you
okay.
meant by distance.
We're best friends already.
Yeah. So yeah, by distance. Okay, by distance. Am I near you?
That depends on your perspective.
Depends on your perspective. Compared to my distance from the sun, am I near you?
We're pretty close.
We're pretty close together compared to my distance from the sun, right? So near is very subjective, and that can be dangerous, because if I'm telling you to look at this function and don't look at what's happening at 2, but to look at what's happening near 2, we can start to have a pretty big debate about what I mean by near. So for this class, and to keep your sanity, I want us to just use the idea that getting really close to something is something we can all kind of agree upon. So like, if let's say we have the number 2, and I wanted to pick a number that was really near 2, what would be a number that we could all like kind of agree upon is near 2? Like, would you all agree that 1 is not near 2?
Like 1.9?
Okay, 1.9, right? Like there's a number right there, 1.9. That's pretty near. What would be a number even closer?
Ooh, 1.99.
1.99 would be
1.9 repeating.
Yeah.
1.99, 3 nines.
1.9999, so on and so forth.
Oh shit.
2.1.
Did you just say 1.999 repeating is really, really close?
Yes.
Okay, you just opened Pandora's box. Yeah, you opened Pandora's box. Can we just try and shut the lid for just a moment, and maybe I'll get back to it at the end? I want to get back to it, but we need to address that, just not quite yet.
Not go to the infinitesimal yet?
Well, just hang tight. You'll see. You'll see. So 1.9 was pretty close. 1.99 was even closer. 1.999 was even closer. Someone said 1.9 repeating, and I'm saying no, wait, okay? Let's just stop at 1.999. Can we all agree that that's pretty close to 2? Just be happy with that?
Yes.
Even though someone may argue, no, 1.99 with a million nines is even closer. Got it. We have to stop somewhere, okay? We have to just, if you want to know how we do this rigorously, then become a math major, and we have a precise way of doing this. It's called delta epsilon proofs. It's a whole other ball game, and unless you're a math major, we're just going to say near is what we all agree upon in here. All right. Any math majors?
I am.
Okay. So if you are, that's a conversation you might want to come to my office, and we can try and get through that. But trust me, you'll have time later to absorb it. All right. But it's a good conversation to have. Okay. So back to this function. We're looking at it. I don't care about what's happening at 2 anymore. We already know what's happening at 2. At 2, it's 8. I want to know what's happening near 2. So by looking at the graph, can you tell what's happening? Just look at this graph. Can you tell just by looking what's happening near 2? So if you took a number really close to 2, like 1.9 or 1.999, if you were to take that and plug that into the function, what does it look like your y values are getting close to? So if I take a number like right here, 1.9, let's say, and I plug it in, and I'm not going to get 8 out, right? It's not going to spit out 8, but would you agree that it's close to 8?
Yeah, be real
Yes.
close.
Yes.
Close. And if I got even closer to 2, do you agree that my answer would get closer to 8 also?
Yes.
Yeah.
The closer I got to 2, it looks like the closer the answer gets to 8. You understand that idea? I'm going to clear this out and I'm going to show this to you visually now, like with an animation. So if we come marching in from the left-hand side, okay, and the blue represents the x value, and this purple represents the y value, then what we're doing is we're marching along from the left-hand side. The x value is getting closer and closer to 2, 1.6, 1.7, 1.8, 1.9, and look at the y value, 7.581. It gets closer and closer. I'm gonna keep marching. 1.91, 1.92, 1.93, 4, 5, 6, 7. I'm gonna go even, oh, hold on. That one. Oh, wrong one. 1.99. See how close it's getting to 8? We're now at 7.95. $1.999. Let's go 3 nines. Real close to 8, right? Now you don't need me to show that to you. Could y'all see that from the graph? Just that the graph was doing that, like it was heading there, heading up towards the 8 from the left. What's happening on the right-hand side? If we approach from the right instead of the left, or do we have the same thing happening? So watch, I'm going to come in from the right this time. I want you to pay attention. The blue is going to be, sorry, the black is the x value. So these numbers are bigger than 2, right? And they're coming in. So I'm at 3.2, 3.1. Now we're at 2.9, 2.8, 2.7, 2.6, right? We keep on getting smaller, but look at the y value. It went up past 8, and now isn't it coming back down towards 8? So from both sides, right? From both sides, the left and the right, it appears that we are approaching 8. Look, don't overthink this, okay? But I need to make a distinction. With this particular function, at 2, the value was 8. As we approached 2 from the left, the function was approaching 8 also. As we approached 2 from the right, the function was approaching 8 also. So this is like the perfect situation. At 2, it's 8. From the left, it's headed to 8. From the right, it's headed to 8. Let's look at a different problem because this is kind of boring. This is a piecewise function. So piecewise functions, don't freak out about them. All they are really 2 functions that have been pasted together. And when you plug a value in, you have to determine which of the 2 pieces you're plugging into. So what I'd like to ask here is, what would f of 2 be? So if I asked you to plug 2 into this function, would you plug it into the top one or the bottom?
Top.
Because of this inequality right here, right? That inequality says less than or equal. So if x is less than or equal to 2, then we're going to plug it in here. And what happens when you plug 2 into this? You plug in 2, you get
8, right? It's the same as the
you get 8, same answer as before, right? So if we're just doing college algebra and we're just looking at what's happening at 2, the answer is 8, right? No difference from the previous problem. However, if we now look at this from a more calculus perspective and we don't care about what's happening at 2, and we try and look at what's happening from the left and from the right, 2 different things are happening. Do you all see that? From the left, if I start moving in from the left, right? I'm approaching 2 from the left. Where's the function headed? What value is it headed to? Let me ask someone. Melina, is it Melina? Am I saying that right?
Yeah, you said it right.
Okay, so Melina, you're the first person I'm calling on. So as I come in from the left, where is the function approaching? What is it headed towards? Can you tell?
It's heading towards 8 again.
It's headed towards 8. Everyone agree? Now, it's not technically ever going to get there, but that's not important. It's what it's headed towards. And that's something we've never talked about before. In college algebra, pre-cal, we never talked about, oh, getting close to this, where's that headed? We never used that language. This is a calculus thing. All right, good. Melina, you want to try the right? Tell me where it's headed from the right, Melina. So I'm going to come in here. Here it is, coming in from the right. It's headed to, goes up a little bit, and then it starts to dive back down. And where does it look like it's headed towards?
2.
Well, it is headed towards 2 from the right, but what's the y value headed towards on this thing? Can you tell? It's kind of hard to tell.
Oh, there it is. 4.
4. It looks like it's headed towards 4. Do y'all see that? 4. So from the left, it's headed towards 8, but from the right, it's headed towards 4. And Melina, I'll keep you on here.
I have a
Melina.
quick question.
Yes.
You said that on the left, it won't ever actually get to 8. Why is
It
that?
doesn't have to get to 8. It doesn't have to.
Okay, I thought you meant
It
it
doesn't
never will.
have to get to 8. It may never get there. What I'm saying, Maddie, is that if the value you're plugging in, 1.9, 1.99, 1.999, right? As long as if that value is not 2, then you're never going to get to 8. You only get to 8 at 2.
So then what about on the right? Because you already surpassed 4.
Sorry, say again.
Well, sorry to interrupt. I said, so what about on the right then? Because you already surpassed 4 coming up and you're going back down towards it.
Well, we looking at the x value, right? The x value is we're coming in this way, and our x value is approaching 2, but from the right. Our y value is this number right here, 4.47. So look at how high that goes. It goes up to 5, right? But see, Ethan, we're not close to 2 yet. We're at 2.63. So we need to get closer to 2. We get closer to 2. Now the y value is dropping back down, and the graph looks like it's approaching what? Somewhere around 4. So it doesn't matter that we went up and then came back down. It's what's happening near, and that's the thing that makes it so tricky. What's happening near 2. So it can do all sorts of crazy stuff out here, but it's what's happening as you get closer, closer and closer and closer, closer and closer and closer. Any questions? Let's look at another one. See if we can do this one without actually plugging anything into the function. Let's just look at it. Hunter, are you there?
Me?
Yeah, I think Hunter, let me see, where are you? I heard you, I didn't.
I'm right here.
Oh, there you are, Hunter, yes. Yeah, Hunter, my question to you is, by looking at this, can you tell me what f of 2 is without like plugging anything in, not even using this? Can you just tell me by looking at what the function's value is at 2?
Looks like it's 6.
It looks like it's 6. Does everyone see that? When you plug 2 in, you have this solid dot here, that's 6. So f of 2 is 6. Good. All right, Hunter, now let me ask you, if I ask you to look at this more from like the take off the algebra glasses and put on the calculus glasses, and I ask you to look, ignore what's happening at 2, and tell me what's happening as you come in from the left, approaching 2, Hunter, where are you headed?
Looks like it's approaching 8.
It's approaching 8, right?
Mm-hmm.
So everyone see that? From the left, we're approaching some y value that appears to be about 8. And Hunter, from the right?
Looks to be approaching 4.
Approaching 4. So we're getting closer and closer to a y value that's around 4. Good. Does anyone need clarification on that? We have 3 things we're looking at. What's happening at the point, that's college algebra. What's happening from the left and from the right, those are 2 other things we're looking at. Those are calculus questions. So I want to kind of recap by looking at the three problems we started this with. This first one, the value of the function at 2 was 8, right? The value of the function at 2 was 8. From the left, it's 8, right? Approaching 8. From the right, it's approaching 8. That was like the holy grail. Everything was happening perfectly there. At 2, it was 8. From the left, it's 8. From the right, it's 8. This one, at 2, it was 8. From the left, it was 8. But from the right, it was 4. So it's like 2 of the three things matched, but one of them wasn't the same. Understand? And then this one, at 2, it was 6. From the left, it was 8. And from the right, it was 4. So like none of them matched. Do y'all see that? Okay. I'm looking at the time. All right, so we have more to do with this. I want to address the 1.999. But I also want to address something else. So trying to figure out which of these makes more sense. Let me do the 1.999. I don't think we're quite ready for the other thing I want to show you. All right, so we were talking about, okay, so this is like off topic, on topic sort of thing. It's random information. You won't need this, but it's kind of a cool little result here. So we were trying to get close to 2 and we were coming in from the left. And so someone said, yeah, 1.9, then 1.9, or sorry, 1.99, then 1.999, and then someone said 1.999 forever, right? I don't remember who said that. Was it Daniel or was it Hunter?
Yes, sir. It was
okay,
me.
so Daniel said 1.999 seems like the number that would be right next to 2, right? Like it doesn't seem like there could possibly be any other number closer to 2 than 1.999. Would you all agree with that? I mean, it seems logical to think that that's the closest number to 2 that you could possibly ever find.
Seems right.
Seems right. Okay, so watch. I'm going to show you something. I want everyone to just follow through this logic. You just tell me if if I do something that you don't like, tell me I don't like that. I don't agree with that. Correct. So I'm going to start off. I'm going to say let x be equal to 1.999 forever. Okay. Anyone have a problem with that? I'm just signing a letter to the number that Daniel mentioned, 1.999. We're good? All right, now what I'd like for you to do is I'd like for you to multiply x by 10. Okay, so when you multiply a number by 10, what happens to the decimal point?
It moves over a place.
It moves over to the right one time, right? So if you multiply 2 by 20, 2 by 10, you get 20, right? Multiply 7 by 10, you get 70, right? All you're doing is moving the decimal over, right? So does anyone have a problem with me now writing this? So not 19.999. Doesn't matter how many 9s I write because they go forever, don't they?
Yeah.
Anyone have any problems with that? Okay. Next thing I'd like for you to do is I'd like for you to ask, or for you to tell me, first of all, what is 10x take away 1x? So if I were just to ask you algebraically, what is 10x's take away 1x from it? How many x's?
9x.
9x. Okay. Now, in terms of what we just wrote down, what was 10x?
19.99 forever.
999 forever. Okay, so if I subtract from that x, which is what?
1.99
forever, what would happen?
You'd have an even 18, wouldn't you?
Yeah, so look, don't the 0.99s kind of kill each other off the whole way down? And then you just have 19 minus 1, which is what? 18?
18.
18.
Okay, but see, these have to be equal, right? I mean, if I say X is this and 10X is that, algebraically, you subtract them, you get 9X, but when you actually subtract them, you get 18, which means that 9X has to be 18, which means that X has to be what?
2.
2, which means, Daniel, that 1.9999 forever is actually the number 2. This isn't like smoke and mirrors. I'm here to let you know that. Okay, sorry. But 1.999 forever is not the number right next to 2. It is the number 2. And so is if you were to take like just the number 0.999 forever, well, that's 1. There's no number between those two. They are identically the same number. Now, if you don't like that, I understand why. Okay, I understand. But here's another way I can kind of try and illustrate this. If you have a number line, and if you have 2 distinct points, right? Let's say we have 2 distinct points, whatever they are, A and B. I can always, 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 always find a number that's right in the middle of them. And the way I can do it is this. I take the 2 numbers you gave me, I add them up, and I divide by 2. In other words, I take their average. And their average will always be the number right in the middle. If you don't believe that, just do an example for yourself. If you take, let's do something easy. Let's do 1 and 7, all right? The number right in the middle of that should be 4, okay? Because there's 3 to the left, 3 to the right. But a way you could have gotten that 4 is to take the 1 plus 7 and then divide by 2. So you get 8 over 2, which is 4, which is the number in the middle. Understand? So when you look at the number, if you take 1.999 forever and the number 2, then if you were to try and do their average, right? Like try and find a number in between them, it doesn't exist. Maybe we should try it. I don't know. I don't know how this is going to work. Take 1.999 forever and add 2 and divide by 2. And that's going to be 3.999 forever over 2. And that's actually 2. People debate this. All I want you to know is there's no number between 1.999 forever and 2. So the 0.99 forever, basically, there's no way to find a number between the two. So it's the same number. And I think I've made that clear, hopefully. If you don't like it, it's okay. I didn't like it when I first saw it.
The way one of my older teachers taught it that kind of helped me remember it is that like because when you do the 9 repeating, it's basically saying that like you're getting infinitely close to 2. And it's like if you're getting infinitely close to it, it becomes 2 at that point. The same way that like when we're doing the when you were sliding the points earlier, it's like you're getting infinitely close to that other point, and then at some point they become the same, and that's what we're trying to look at. That's kind of the same concept.
Yeah, the 0.99 basically just says you keep on moving closer and closer and closer and closer. And so you might make the argument, well, you'll never get there. But the thing is, the idea of doing something infinitely many times, you can't do that either, right? So like if you try to get on your calculator right now and figure out what 3.999 forever is divided by 2, you can't do it because you got to hit 9s forever. So it's a tricky thing, but this is kind of where calculus leads us. We get into some murky waters here, you know, and there's this other idea that I don't really have a lot of time for, but just the idea of infinity itself. Like everyone here has heard of infinity, but there's actually 2 types of infinity. And so we have to kind of put our heads around that. We'll talk about it, I'm sure I will, but I don't want to say anymore because we're out of time. So what do I want you to do tonight for homework? I definitely did not get very deep into this. So why don't we make today's assignment. Let me bring up the actual book here. Why don't we make today's assignment for you to just maybe go back and look at the 1.1 and 1.2 and just kind of look at the problems in that section. I'll send them to you if in case WebAssign's not opening. I'll send these to you and you just kind of like play with the problem, see if there's something that, you know, like, oh, you know, that's really something I'm not familiar with, and just play with that. I don't think we have enough for you to like constructively go through 1.3 homework at this point. We need to develop a lot more, but I think we've got our feet on the ground. We're moving in the right direction, and you know, we'll get on pace. We'll get on track. Okay. All right. So you're
Hell
free
yeah.
to go, and I'm gonna stop.